Chem 1251 pre-lecture video, Limiting Reactants. It's my birthday! Bake me a cake! Okay, it's not my birthday, but let's say that it's your friend's birthday and you'd like to practice your chemistry skills in the kitchen, so you try to bake a cake. You look up a recipe and find that you need 1½ cups of flour, 2 eggs, a ½ cup of butter, and 1 cup of sugar to make a cake. This doesn't mean, however, that you have exactly 1½ cups of flour in your pantry or 2 eggs in your fridge. It just means that if you have 1½ cups of flour, you should use 2 eggs. Uh-oh, you actually have only 1 egg left in your fridge, but you have more than enough flour, butter, and sugar. Because you have only 1 egg, the amount of cake you can make is limited by that egg because you'll run out of it before you run out of any of the other ingredients. In this case, we can't make a whole cake, but just this one poor slice. This predicament occurs very often in chemistry, where we call the substance we run out of first the limiting reactant. The idea of limiting reactants answers some questions raised by stoichiometry being the conversion of masses to moles and vice versa using a balanced chemical equation, such as how much product is going to form and how much of a reactant to initially put into a reaction to get a certain amount of product out. We'll define the reactant that runs out first. Note that this has to be a reactant as the limiting reactant or limiting reagent. If we have more than enough of the other reactants, those will be called our excess reactants. The maximum amount of a product we can make is going to be related to that limiting reactant, and this maximum of product is called the theoretical yield. It is important to remember that our balanced chemical equations tell us only the ratios of how much reactants get used up compared to how much of our products get made. Just like the case with the cake, the recipe doesn't necessarily tell you how much to actually use, but just the proportions in which you should mix the ingredients. If you want twice as much cake, you need to double the amount of all of your ingredients. So the recipe, or in our case, the chemical equation, just tells us the proportions. Let's look at another cooking example that's a college staple, grilled cheese. As a poor college student, you can whip out your George Foreman grill and slap on 1 slice of cheese between 2 slices of bread to make a grilled cheese sandwich. Just like a chemical equation, we can represent this with coefficients and symbols, but this again just tells us the ratio of bread to cheese. But what if your cheese is getting moldy and you want to use up everything in your kitchen? Let's see. We have 7 slices of cheese and 10 slices of bread, so how many sandwiches can we make? In this case, we can only make 5 grilled cheese sandwiches because we're going to use up the bread first. Even though you can probably figure this out in your head, let's write down the process that you actually used. If you were to use up all 7 cheese slices, you can make 1 sandwich per slice of cheese to make a total of 7 sandwiches. If you were to use up all 10 bread slices instead, however, because the equation gives us the ratio of 1 sandwich for every 2 slices of bread used up, you could only make a maximum of 5 sandwiches. This lower number means that bread will run out first, so bread is the limiting reactant, and the 5 sandwiches that we have is our theoretical yield. If you have a part-time job as a caterer, however, you don't have just sliced cheese and bread, but rather you get wheels of cheese and loaves of bread, and you need to cut those up yourself. So how much are you supposed to order? We need to convert from wheels of cheese to slices of cheese and loaves of bread to slices of bread using conversion factors. Then figure out in each of these cases how many sandwiches we can make. In this case, our bread is still the limiting reactant because we can only make a maximum of 30 sandwiches as our theoretical yield. This is very similar to chemical reactions, where we can't measure out numbers of atoms or molecules, but rather we have to measure out gram quantities of our reactants and convert them to numbers of moles of reactants. As an example, in the Haber-Bosch process, nitrogen gas and hydrogen gas react in a 1:3 ratio to form ammonia. If we start with 1 gram of each reactant, let's first assume that nitrogen reacts completely. The grams of nitrogen can be converted to the moles of nitrogen by dividing by the molar mass. Then the mole-to-mole ratio from the balanced reaction tells us that 2 moles of ammonia are formed for every 1 mole of nitrogen used up, telling us how many moles of ammonia that can be formed. Finally, using the molar mass of ammonia helps us find the number of grams of ammonia that can be formed if all of the nitrogen gas gets used up. In a separate step, let's assume all of the hydrogen gas gets used up and ignore the nitrogen. Similarly, we can use the molar mass to find the number of moles of hydrogen used up, establish a mole ratio from the coefficients of the equation to find the moles of ammonia that could be created, then we multiply by the molar mass of ammonia to find the number of grams of ammonia that could be formed if all of the hydrogen gas gets used up. Comparing the amounts of ammonia we could make, the smaller number is the maximum amount that can be produced and corresponds to the amount made if all of the limiting reactant is used up. This maximum amount of ammonia is called the theoretical yield, and in this case, the nitrogen is the limiting reactant.